Are ready? Good. Hello, everyone. Let's get started. Today, we do not have Professor Mutlu. I'll try my best to substitute for him. I'm Giray Yalıkçı. I'm a researcher and lecturer in Safari Group. I recently got my PhD on memory robustness. So I'll talk about the rest of the memory robustness today. Professor Mutlu already covered the essential things in the last week, but we will elaborate more on the story of memory robustness and the today's concerns and tomorrow's concerns. There are many, so our main focus will be on RowHammer, but we can extend the problems that we talk about RowHammer to other vulnerabilities in the memory devices. So RowHammer is something that is used by a lot of security exploits. You can use RowHammer to take over a system, read data that you don't have access, read access to, permission to. You can break out the virtual machine sandboxes. You can corrupt important data. You can change critical workloads behavior. You can steal some secret sensitive data like your SSH keys, for example. RowHammer story pretty much starts with this particular paper from ISCA 2014. It was from Safari, Flipping bits in memory without accessing them. We will talk about this paper in detail later on in this lecture. But I'll first talk about the immediate impact this paper had in the field, which is a paper from Google folks that exploits this RowHammer vulnerability, the inherent RowHammer vulnerability that DRAM chips have to gain kernel privileges in Linux systems. So it's from the Project Zero team in Google, and they exploit RowHammer to gain kernel privileges. So this is an assembly of our slides merged with their slides. So this is what that paper talks about. You can see the reference in the bottom here. RowHammer is a problem with some recent DRAM devices in which repeatedly accessing a row of memory can cause bit flips in adjacent rows. So this is what we showed in ISCA 14 paper, right? So they already cite that paper, and then they test a selection of laptops that use some modern memory devices of that time, and they found that the problem persists in the problem exists in some of them. And they built two working privilege escalation exploits using this effect. And they basically end up exploiting RowHammer to gain kernel privileges and take over a system, basically. So how they do it is that they use these RowHammer-induced bit flips to alter some critical bits in the system that can, in a Linux system, that can give them the unprivileged, they give them access to some unprivileged regions. So when they run this on a machine that's vulnerable to RowHammer, they can actually flip bits in page table entries that I will talk about this in detail. And this allows them to gain read-write access to the whole physical memory. So this is, the following slides are going to be some slides that we borrowed from the Black Hat presentation of Google Project Zero. So they define this as like a page table targeted kernel exploit. So page table entries are dense and trusted in the software level, but when we exploit physics, then software level trusted data structures might not be that trusted. So they aim to get access to the page table that gives access to all of physical memory. And they maximize their chances by spraying physical memory with page tables, and they check for useful and repeatable locations in the memory that are vulnerable to RowHammer. So this is, this is a recap of your computer architecture knowledge or virtual memory or OS knowledge. So we have, when we call page table, often a 4 kilobyte page containing an array of like 512 different entries. And this is what we have inside every entry. So we have a physical page base address and then some control bits here. So for example, we have some read-write permission bit here. So if we want to flip this bit so that we can get a write permit to a page table entry, it's like, let's say we have the chance of having a bit flip in a given location is uniformly distributed in this page table entry, let's say. Then the flip in this permission bit has like 2% chance, right? So they do not do that. What they do is they flip bits in this physical page base addresses, so that you have 31% chance of hitting one of those bits, so that your page table entry actually points to a different location, which you shouldn't be able to do. So let's see how it works. So you have a virtual address space in your machines. You have an infinite memory from the software's point of view, right? And you have a limited physical memory. So when you allocate some pages in the virtual address memory, they point to some physical memories. So if you allocate, okay, so to access here, you basically access a virtual address. That virtual address, the operating system on behalf of you accesses some page table entries, and then with redirection from those page table entries, you access to the correct physical memory location. So what happens if you allocate different places in your virtual address space that point to the same physical memory? You have multiple of these page tables, and then they keep pointing to the same physical address. So this happens when you use shared libraries, for example. So what they do as part of the attack is that they keep allocating a lot of pages in the virtual address space that point to a physical page. So if you do this in an aggressive way, you can actually fill up pretty much all of the physical memory with page table entries. So let's say you access to this virtual address, and then it goes to this page table entry, and then it points to here, right? So let's say you have bit flips in this page table entry, the physical page number in this page table entry. Then it goes to a different location. And if you fill up all your memory with page table entries, then the new location that this points to, it has some other page table entries. And let's say you have allocated some memory space with read-write permission already, then you have write access to this page table entry. Now you can change the data inside there. And the funny thing is, you can just make it point to any arbitrary location in the physical memory, right? So what you do later on, you access to the other virtual, like this virtual address, virtual page. And then this points to this page table because it thinks that there is the original page table there. And then since you altered the information inside this, you can access to an arbitrary location and you can write the whole memory. And then by doing that, you can actually take over the system. So this is just like the summary of what they did. So they allocate a large chunk of memory, search for locations prone to flipping. Go ahead. Yes. In a naive method of, okay, maybe I need to repeat the question, right? So the question is, can we limit the number of page table entries so that we can mitigate this kind of attack? You can do it to some extent. You still need this virtual memory support, so you cannot completely eliminate it. By limiting the number of them, actually effectively limits the number of physical cells you can exploit in the physical memory, right? And they have some improvements on top of the existing attack on top of that, actually. So you can say that you cannot create like more than n page tables. Of course, it has like performance overheads and all that, but I'm not getting into that. you can still find the vulnerable bits inside the physical memory, and then you can target your attack to there with using like smaller number of page tables. They actually show that in this presentation. I'm not sure if I have those slides here, but if you go to the original presentation, they explain all of them. So they check if they fall into the right spot, meaning that do we have the exploitable bits in that page table entry, and then they return that particular area of memory to the operating system, so that they force the operating system to reuse that location for the page table entries. So this is actually sort of an answer to a previous question as well. So they cause bit flips in the page table entries, they change the address, and then they abuse the read-write access to the whole physical memory. So, okay, we have some of these like fancy images throughout the slides. It has been quite popular in the security community, and there are like all sorts of like different RowHammer images you can see like this here and there. So this is more like a popular science kind of description of RowHammer. So it's an analogy, basically. It's like you break into an apartment by keep smashing the neighbor's door until the vibrations through the wall propagate and open the door that you're after. So after this first exploit that Google Project Zero showed, of course, it's something very useful. So it's essentially an asset or a tool to have this RowHammer vulnerability inside modern memory chips. It's provided the necessary necessary functionality for the security folks to exploit it in many ways, right? So the first exploit was by using some C++ code. Then security experts figured out a way that they can just run some JavaScript code and they do the same thing. So what does that mean? You just like visit a web page and then it runs a JavaScript code and your computer is compromised, right? So it's quite interesting. They have ways of hammering and rooting Android devices because they also use the same technology, right? There are many works in the field that use like different components in the system to make your attacks more effective, faster, more efficient. So there are works that show that you can actually use GPUs to access the main memory, and then you accelerate the way that you induce the bit flips, so you can conduct your attacks in a much smaller time window. There has been some. So if you remember the code that we showed last week, it's basically like you access two memory locations, and then you have two instructions like CL flush that evict those data from the cache to the main memory. So for a while, people were thinking that, okay, yeah, if you disable CL flush in the system, then there's no vulnerability. But there are papers that show that you can use some memory accesses that are not cached at all. You can directly access to memory. So for example, these papers use network packets. So in your system, you have a network chip that connects to the processor, and it goes through the direct memory access engine to directly go to the memory, right? So you don't put those data into the cache. So you don't need to have CL flush for this, for example. So you can just use network packets to even attack a machine that's remote. These works are showing that. And yeah, another network-based RowHammer attack. So this is quite interesting. So the experimental characterization data of RowHammer vulnerability so far showed that the bit flips are repeatable in certain locations. And they're also quite sensitive to the data pattern you put inside those DRAM cells. So what data, like 1 or 0, you have in a DRAM cell, and what data you have in the neighboring DRAM cells matters so much that you can actually craft a data pattern to focus your attack on particular cells. So what this work does is that this is called rambulate. They read bits in the memory in the locations they don't have access permission without accessing them. What they do, they initialize their own memory space with some particular data pattern, and then they keep hammering the sensitive data by accessing to that row by accessing some other columns that they can access. And then they observe the bit flips in their own data. So it's, since we know that the data pattern sensitivity is quite significant in RowHammer, they can actually read your RSA key, basically, the key that you use for SSHing into some machines. So it's quite scary, and it was published in 2020. There are works, two works actually, that came in 2019 and 2020 that show that you can induce bit flips in a guided way, again, to some weights in some neural networks. So it was the top of the hype of, maybe not hype, the deep neural networks, right? It's quite popular in many workloads. We use deep neural networks. And then they come and say that I can flip bits inside the weights of your DNN, and then I can reduce your DNN's accuracy from 90% to 10%, so that it's pretty much useless. If you're using this DNN to self-drive your car, for example, then you can understand a pedestrian. You can misdetect a pedestrian as a, I don't know, that as if it's not there, and then you can hit, for example. There are like significant safety issues that you can guess here. There are works that use, again, different components, like so this particular attack is using the FPGAs. So you have in many systems, they are connected to some FPGAs for as accelerator purposes, right? So you can actually use those components to accelerate your attack. You can induce bit flips in a much faster way. In 2021, Google again came up with another attack called half double. It was a security blog post, and then it became a paper in the top security when you're using security in 2022. That basically shows that you can even do induce bit flips in an easier way by hammering rows that are not next to you, but in 2 rows distance. Yeah, I just wanted to mention that. So okay, here's another like story from the field. So if you go and watch the presentation of the Google Project Zero that I mentioned in the beginning, at the end of the presentation, they talk about 3 mitigation methods. One of them is error correcting codes. How many people heard about error correcting codes here? Oh, quite. Okay, quite some. Nice. So you guys are familiar. So if you're in your data, there's a bit flip for some reason, you can use these error correcting codes to correct those bit flips, right? And they come with some parity bits, basically. And they have some limited capability of, like, let's say in a 64-bit data word, they can correct some ECC scheme can correct like 1 bit, for example, or detect 2 bit. In some sophisticated ones, they add like more parity bits, so you keep consuming your system's resources to be able to correct more bits. So there's a whole trade-off space there. And a quite popular one is the single error correction, double error detection, Hamming code that is used in many systems. And in this paper, yeah, before this paper, they were talking about like, not they were talking, there was a like general understanding of, okay, if you have ECC, you can actually correct RowHammer bit flips because they happen like here and there. They're not like very concentrated in a sense. So ECC solves RowHammer. And this paper in 2019 showed that ECC does not solve RowHammer. Actually, you can, in an ECC protected system, you can reverse engineer the ECC. You can guide the bit flip locations in your DRAM cells in a way that you can actually cause silent data corruptions. Silent data corruption means that your ECC does not even know that there's a bit flip there. Later on, there has been some works that from DRAM manufacturers that they implemented some mechanisms inside their DRAM chips, and they claim that their DRAM chips are RowHammer free at some point. And then, of course, as researchers, we investigated those. I'm just showing this paper here, but I will talk about it in detail later on. So I just wanted to say that a key result from this paper here is good for mentioning that. You can, in modern DDR4 chips with RowHammer protection, you can do the reverse engineering. You can craft access patterns that induce bit flips, and you can induce up to 7 RowHammer bit flips in an 8-byte data word. So in 64 bits, you have 7 bit flips. So to protect against this kind of error rate, you really need to have like, you need to span a lot of parity bits basically. So ECCs, or today's ECCs, are practically ineffective against RowHammer. So there are many security implications. I tried to cover some of them. So they reach to a point that you actually hate your DRAM chip and you want to smash it with a huge hammer. Okay, so there are some works from Professor Mutlu that actually summarizes like retrospective survey and futurespective, what's that? Like future-looking papers as well that show about like the current and future problems and what research problems to work on. So this is one of them, a retrospective paper from 2019. There is an updated version of this that we published in 2023. And another very short retrospective paper that is invited to the 50th year anniversary, 50th year of ISCA conference. ISCA is one of the top conferences in the computer architecture field. So basically, you can recognize the title of the paper. Actually, this is a recognition of the 2014 paper because of the impact it had in the field. So there's a short summary of that paper and the paper's impact and what happened until the 50th year of ISCA. I also wanted to mention here some recent advancements in the RowHammer field, but we will talk about these, like this is just like a foreshadowing it. We will talk about all of these later on. So Samsung in 2023 published a paper that shows that their in-DRAM mitigation mechanism, they explain their in-DRAM mitigation mechanisms. And like 1 year after that, basically, there's a Google paper that breaks that as well. And I want to show this paper as well. This is very relevant. It was published just like 2 months ago in Using Security Conference, one of the top security venues. This is actually from ETH Zurich. You can see the names. That shows that you can even get bit flips in DDR5 modules, which is the state of the art now. So the problem is still there. And I want to promote my thesis again that has a summary of these and also includes some cutting-edge research projects in it. Okay, so I'll continue with understanding RowHammer. So we did a lot of experimental characterization, and I'm going to cover all those now. But before going to that, are there any questions? Yes. Correct. So okay. So the question is, does the attacker need to run a code on the victim system so that they can induce some bit flips, right? So yes and no. So isolation is a good solution for security and for RowHammer as well in general. but it comes with some practical costs as well. So can you point to a system that never connects to internet, for example? There are systems like that, of course, but for like other functionalities, you usually want everything to be connected. Yes. Yeah. Yeah. So that's where I was coming. Yeah. So let's say we are talking about a computer. You open a web page that runs JavaScript code. You have a code running on your system. If you have if you have access some network connection to some system, you can send some network packets. Then you can do like network-based attacks. Of course, if you just like isolate everything, then no malicious user can run any program on your system. Security-wise, you might be safe. I have to mention though that the RowHammer vulnerability is getting worse. We will see it later on. That fewer and fewer row activations cause bit flips nowadays. So it actually constitutes a reliability issue as well. And when we look at the benign workloads in the field, they already unintentionally basically keep hammering DRAM rows. And so in a refresh window, for example, you can see some benign workloads that reach the activation counts of like several hundreds, even like close to 1,000 if you go for like some particular workloads. And you can now like induce bit flips in like several hundred activations at the same time. So you might have some like unintended bit flips popping up in your system as well. So that's another issue. Other questions? Okay. So let's go with the understanding RowHammer papers. The first one is Philippine Bits, that the paper that I referred to that was published in 2014. That ran a lot of tests on real DRAM chips. So this is a picture of our infrastructure that we used for that set of experiments. So as you can see, there are like in a plexiglass container, there is like a bunch of FPGA boards here. There are some DDR3 DRAM modules that are connected to them. It's DDR3 because these tests were conducted in 2012 and 14, the DRAM of that time. And you have some host machine that is connected to these FPGA boards that run these tests, collect the experimental data, processes it. And we have a commercial temperature controller here that we set the temperature, and then it runs this heater on these plexiglass containers, essentially heat chambers, to heat up the chips so that we can test our chips in different temperatures in a stable way. In this work, we tested 129 DRAM chips. They were manufactured from 2008 to 2014. And you can see like they are from 3 major manufacturers, and you have all the information in the full paper about these DRAM chips. So to summarize the characterization results, essentially, most modules are at risk, meaning that we can induce bit flips in these modules. And you have this trade-off based on that data. You either need to use vintage DRAM modules that are like manufactured, basically essentially older DRAM chips, or you have to deal with errors. Because in newer DRAM chips, we have the scaling in the technology node, and DRAM cells are smaller. They have a smaller charge. They're closer to each other. So this interference or this disturbance effect is exacerbated. And a key point is adjacency. So basically your aggressor row and the victim row should be physically close to each other, if possible, adjacent to each other. Because as they get closer, the disturbances exacerbates again. And we have some sensitivity studies and other results in the paper, and we also discuss what kind of solutions that can be used for mitigating such bit flips. So here is yeah, this is a nice plot where on the x-axis we look at the distance between two rows, the aggressor row and the victim row. So distance of 0 means the aggressor row itself. So we keep hammering the rows in the location 0 here. And then on the y-axis, it's the bit flip count. So you see like how many bit flips appear in each row. So as you see, like most of the bit flips are concentrated in the immediate adjacent rows, and you can also have some bit flips in the close proximity, non-adjacent rows. So most aggressors and victims are adjacent to each other. So we look at how the access interval of the aggressor affects. So how frequently you need to hammer, basically. So the highest frequency you can activate a row is one activation every 55 nanoseconds. This is a timing constraint by the DRAM communication protocol, DDR3 of that time. You cannot activate a row more frequently than 55 nanoseconds. And if you make it like make activations very frequent, then you have the highest bit flips. If you reduce it, then you have less and less bit flips. So it reaches to 0 around like 500 nanoseconds in this plot. Of course, this is data from the DRAM chips from 2008 to 2014, right? So nowadays, if we regenerate this plot with modern DRAM chips, then these slopes will be much more flat, basically, because at larger access intervals as well, we still have a lot of bit flips. Okay, go ahead. Because basically you send activations to the aggressor row, right? And so here we look at sensitivity of like how frequently we can send activations and how many bit flips we can get by doing that. So there is an upper limit of the highest frequency, because once you send an activation command, the memory controller does not allow you to, well, in this case, we don't have memory controller actually, but by the DRAM communication protocols, they mandate some timing constraints. So after you activate a row, there's a time window that you need to keep that row active for. And then you can close that row. And after sending the closing command, which is pre-charge, you need to wait for the latency of that pre-charge operation as well until you send the second activation. So the minimum time window between two consecutive activations is around like 55 nanoseconds. So it's not, so so you're looking at realistic cases. In this case, you cannot send basically activations sooner than 55 nanoseconds. Yeah, so if you go to any system, they have their own memory controllers, and all these timing constraints are enforced in those memory controllers. So you cannot, so it's not relevant basically to look at to the points smaller than 55 nanosecond in this work. Later on, we looked at that as well. Yes. So in DDR4, if I remember, the timing constraint is like around 46 nanoseconds. Is correct? Maybe Ismail can confirm. TRC for DDR4. I think I also saw like 46.2, something like that. Yeah. So basically, it varies from chip to chip as well, or based on the generation of the chip. But it's around the same ballpark. Not necessarily. So yes, you can send activations more frequently now, but the reason that it gets worse is that the physics gets worse. The DRAM cells are closer to each other, so one activation actually creates more disturbance than before. So we looked at the refresh interval, basically. So this is the nominal refresh rate. You have, since DRAM chip is volatile, you have to refresh your data inside the DRAM chip every 64 milliseconds, right? So if you basically, based on these experimental data, you can see that if we refresh our chips more frequently, then we have less bit flips. And if we refresh them very frequently, maybe we can get rid of these bit flips. But it's immediately turned out to be quite impractical because refreshing row also takes some time. And you have many rows to refresh. So when you just add up those times, then it needs to be smaller than your refresh window. And you quickly reach to that point, actually. And yeah, so in the based on this data, you need to increase your refresh rate by 7 times, but it's not practical, and you need to refresh even more frequently in today's DRAM chips. Also, data pattern plays a significant role here. So if we have the same, if we initialize the whole DRAM row with ones or with zeros, we have some bit error rate, of course, but when we go for like interleaving data pattern, we increase the bit flip rate, bit error rate quite significantly. Yeah, so almost we didn't see any correlation between the victim cells of data retention bit flips and RowHammer bit flips. So it seems like these are different error mechanisms, and RowHammer errors are repeatable. So if you observe a bit flip at a particular location, in the future, it's very likely that you can observe another bit flip in the same location as well. So you can exploit those bit flips and craft your attacks accordingly. And yeah, in this work, the observation is like as many as 4 errors per cache line. In a 64-byte, let's say, you have 4 bit flips. But later on, as I said, like in newer chips, we have like 7 bit flips in 64 bits. And for a given cell, you can see that it's affected by the 2 aggressors on each side of the victim cell. And this was the 2014 paper. And in 2020, we repeated. Sorry, go ahead. Okay, so what is the reason behind the data pattern dependency? So far, like based on this, I can just say that it's empirical observation, right? But you can actually simulate the physics in your mind a little bit, and once you initialize a row with 1 or 0, like you can do the encoding in either way, but like in one case, you have some high voltage in some capacitor, and you have low voltage in the neighboring capacitor, and it creates some tension, basically, some electric fields. And this whole thing is based on like electrons moving around, getting trapped in certain locations, exacerbating leakage, and reducing the data retention time. So, so far, I guess I can explain like this. Okay, so this was 2014 paper, and we are, what slide is this? 64. Okay, I'm slower than what I was planning to, but I'm going to cover this quickly as well. I'm hoping to reach to slide 75 before we give a break. So RowHammer is getting much worse. We repeated this experimental study and extended it to some different sensitivities as well in 2020. And what we observe is that it's getting much worse. So it's not very surprising at this point because I keep saying that. And there are some works from industry as well. So this is a paper that we collaborated with some Microsoft folks that looked at the RowHammer vulnerability of the machines in their servers. And it turns out that when you ask the question, like, can we guarantee that our systems are RowHammer free? It's very hard to answer that question because you need to really conduct some rigorous experimental characterization there. And we also looked into different aspects of sensitivities of RowHammer vulnerability. In this work particularly, we looked at the temperature, data access path, memory access patterns, and the and the spatial variation within a DRAM chip. And it turns out that RowHammer varies in, it has like multiple sensitivities. and they are not really straightforward to find the worst case very easily. And we also looked at the effect of voltage scaling on RowHammer. We will cover all these works in time. And we also tested some HBM DRAM chips. Hopefully, we will talk about this tomorrow in detail. And we show that it's not only DDRx, like DDR3, DDR4, DDR5. LP DDR series are also vulnerable to RowHammer. HBMs are also vulnerable to RowHammer. And HBMs are quite interesting, or like understanding the vulnerability of HBM chips today is quite relevant because now you know that we have like all these advanced AI models and workloads that run on GPUs and things like that. And all of them are essentially using high bandwidth memory chips, HBM series, basically. And there were not much characterization data in the field, and we did that, and they're not much better than DDR, basically. So your LLM models can be at risk as well. Okay, so we will talk about these papers. I just pretty much all of them in the following lectures and in this lecture as well. And so this HBM work is quite recent. It was published in DSN, which is a top conference for dependability and reliability earlier last summer. And a spatial variation study that I will talk about tomorrow, actually, is also published in earlier this year. And there are some RowHammer solutions, so we are not hopeless in that sense. So the ISCA 14 paper defines some immediate and long-term solutions. Immediate solution is basically you need to update your firmware somehow, and then you should mitigate those bit flips, right? So you aim to protect vulnerable DRAM chips in the field with minimal changes to hardware, let's say. And in the longer term, we focus on improving our hardware inside the DRAM chip and inside the processor. So it has a wider range of protection mechanisms, but it's not immediately applicable to the chips in the field. And ISCA 14 paper proposes 7 solutions that I will cover. But yeah, later on when we classify the solutions in the field, we can see that you can have more robust DRAM chips. Basically, you can improve the physics, which is like quite expensive and time-consuming going forward. This is one way of going there. The second way is like you can increase the refresh rate. So basically, in this plot, it's like the voltage in your cell. It goes lower in time because of the charge leakage, because DRAM is volatile. So if you just like refresh it more frequently, it leaks less. So by doing so, you can hope to avoid RowHammer bit flips. But when you do the math, you can see that it's not very practical today. You can introduce some physical isolation between the physical DRAM regions of a potential attacker and the victim. It's a somewhat practical way, but it requires a lot of isolation rows in between, so you sacrifice your memory capacity. You can observe the memory access patterns. You can detect that one particular row is rapidly and repeatedly being activated, so it's been hammered. So you can go and proactively or reactively refresh the potential victim rows around it, and it mitigates the bit flips. Or you can even like throttle memory accesses so that you do not access to memory at a high enough frequency to induce bit flips. Of course, all these methods have their own like cost, power, performance, and complexity. It's a huge trade-off space. You need to find your solution based on the trade-off across all these. So following our 2014 paper, Apple released a security patch, essentially increases the refresh rate, because that's pretty much what you can do in the devices that you already shipped. And I guess Lenovo also had some security update, but I don't have the slide for that here. And our solution in that ISCA 14 paper, which actually survived until today, the only solution pretty much that survived until today is PARA, probabilistic adjacent row activation. So it's a very low cost mechanism. And the key idea is as follows. So when you close a DRAM row, you refresh its physical neighbors with a low probability. This is the probability threshold basically over there. You can play with this number, of course, to make it more aggressive or less aggressive. So based on this probability, you get bit flips based on the characterization data in that paper. You only get like this many bit, or the probability of your getting bit flips is this much in a year of hammering. And by adjusting this value, you can play with its aggressiveness. So advantages of PARA is that it refreshes rows very infrequently, so it does not incur high performance or power overheads. No, it's for hammering, yeah. So so advantages of PARA is that it refreshes row quite infrequently, so you have low power and performance overheads, and it's stateless, so you don't have to maintain a lot of metadata about your memory access patterns. You can just implement a very low-cost mechanism. You can just implement it very quickly, and it doesn't consume your resources, basically. So it's an effective and low overhead solution to prevent read disturbance errors. And if implemented inside the DRAM chip, which is done today, you basically need enough time slack to perform those refresh operations. And there's plenty of slack today that we showed in like several other papers that we might cover some of them in the following lectures in the following weeks. If you implement PARA inside the memory controller, which is also done actually by Intel at some point, I have a slide about that. You essentially need some coordination between the memory controller and the DRAM chip, because you need to know which row is next to which row in the physical layout of the DRAM chip. So that once you find an aggressor row, you have an idea about like what rows can be potential victim rows. So this is a screenshot of a BIOS screen of an Intel system. So basically, they call this like RowHammer solution. Yeah, RowHammer P. I don't remember what P stands for. So basically, you can either double the refresh rate as a RowHammer solution in your BIOS setting, or you can choose one of these RowHammer activation probabilities to perform those victim row refreshes in those systems. So later on, Intel did not, I think later on newer BIOSes did not have this option after some point, because the DRAM manufacturers came up with new set of DRAM chips in DDR4 time, and then they say that new DRAM modules are completely RowHammer free. You don't have to worry about that. You don't have to do any refreshes. That functionality in some BIOSes are discontinued. But as we will see later on, that it's not the case. You shouldn't believe what the industry is saying blindly, basically. So a takeaway from our study is that main memory needs intelligent controllers for security, safety, and reliability. And it's not only true for DRAM modules, it's also true for NAND flash devices and other memory technologies as well. Especially in flash, we keep observing lots of bit flips, because it's not a very reliable memory technology by itself. And there are a lot of mechanisms that people implement around NAND flash arrays so that you get rid of all those bit flips. There's a lot of redundancy implemented there. And we also have some characterization works on NAND flash. We might cover later on some lectures. So yeah, as I said, like we have two major RowHammer directions. One of them is understanding RowHammer. So we already looked at a lot of effects and sensitivities of RowHammer. but we have other things to do. So if you're curious, I encourage you to come talk to us. We can plan some characterization-based works to understand RowHammer better. And we also need to find better solutions. We need flexible and efficient solutions. We want our solutions to be patchable in field so that when you figure out a new vulnerability, or when you change your DRAM chip and the new DRAM chip is more vulnerable than the previous one, you can easily change the configuration of your solution. And we also need works on co-architecting system and memory. So this is a good logical break. I ran over a little bit, so it's 2:05 now. So I think it's a good point to take a break until 2:15. Yeah, then if 10 minutes is okay, yeah, let's meet at 2:15 now. By the way, before we go, do you guys have any questions? No. Yeah, go ahead. Why do we implement para in the memory controller? Yes, so it came later on. It was not implemented in DRAM chips before, so they implemented in the memory controller, and so that you can also protect the chips in the field, right? But then they also implemented inside the DRAM chips as well. But they came late. That came later. Yeah. So in architecture, it's hard to say that one is better than the other. Usually, there are like different trade-offs. Inside DRAM chip as well, there are some additional constraints and challenges that we will talk about later. Hello, welcome back. Can you still hear me on YouTube? Okay, good. Let's get to more up-to-date times. So we talked about what happened in the field of RowHammer before 2020. So now let's look at what happened since 2020. So the first paper that we will go through, or the set of experimental characterizations, is Robustness RowHammer. So this paper was published in ISCA 2020, which is one of the top conferences for architecture. And in this study, we essentially test more than 1.5K chips. And we show that newer DRAM chips are more vulnerable. This is the main key takeaway from this work. And there's something striking, like until this point, everybody was assuming that you need tens of thousands of activations to induce a bit flip. But this work showed that you can have bit flips at only like 4.8 thousand hammers per aggressor row. So this data, even though it's like something striking, even now it can be stale. You will see towards the end of the lecture that we can actually induce bit flips at much lower hammer counts in today's DRAM chips. So the trend of getting worse is still there. And chips of newer technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. And existing mitigations are not effective at future technology nodes. So we evaluated the existing mitigation mechanisms of that time as well and showed that they incur too high performance overhead. So you end up either having bit flips in your system or having a quite slow system. So this is the set of DRAM chips that we tested in this work from 3 major DRAM manufacturers. In this work, we didn't say their names, we anonymized them. But today, like we actually say that it's like Samsung, Micron, and SK Hynix in more recent works. And this paper covers DRAM modules that implement different DRAM communication protocols, such as DDR3, DDR4, LPDDR4. And it classifies each of these as like old and new DRAM chips based on their manufacturing date or the die revision and the density they have. So here is a plot that I'm not going to go through very in detail. But this shows how the hammer count affects the number of bit flips you have. So each curve belongs to a different DRAM type. So I can use my pointer here. So this blue curve belongs to DDR4 old DRAM modules, for example. And then this yellow one is for DDR4 new. And you can see that the curve just like shifts up as you increase your hammer count on the x-axis. You see the bit flip rate on the y-axis, and the curve shifts up. So it means that you have more bit flips in newer DRAM chips. And it's true across all these like different standards. And RowHammer bit flip rates increase with technology node generation. Here's another key result or takeaway from this paper. So here we implement different DRAM mitigation RowHammer mitigation mechanisms. So you're familiar with PARA now. PARA is the one that I explained the previous lecture, like the probabilistic one that we proposed in ISCA 14 paper. And there were some other mechanisms as well proposed later on. So ProHit and MRLOC are other probabilistic mechanisms that improve on top of PARA. And there's twice that was the state-of-the-art counter-based deterministic solution of that time. And it has a problem inherently in its design. It cannot scale after a threshold of 32,000 for a threshold below 32,000. So we just like assume that those inherent problems are resolved, and we just like scale it as if it works. So that's the curve of twice ideal. And what we see is that as we go from left to right, we reduce the RowHammer threshold, which is essentially this HC first metric, the number of hammers required to induce the RowHammer bit flip. So as you go from left to right, we go from older chips to the newer chips. And you can see the experimental characterization data actually marked there. Like DDR3 old is here. You need like almost 100,000 activations to induce a bit flip. DDR3 new is here. So you have like a few tens of thousands activations. And on the y-axis, we look at the performance overhead of each given RowHammer mitigation mechanism. And as you can see, all the curves are going down, right, as we go from left to right. And this means that your system performance is degraded, and you have some significant performance overheads. And we have a curve here that is called ideal. Ideal is it's a hypothetical mechanism that does not exist. It essentially detects the RowHammer attacks with 100% accuracy, and it performs refresh operations on the potential victim rows only when needed. So it goes like with relatively lower performance overhead than the other mechanisms, and the gap in between the best mechanism of each HC first value basically and the ideal keeps increasing as you see, like these red arrows are getting longer and longer. So it shows us that the existing mitigation mechanisms of the time, which is 2020, were not scaling as expected or as wanted with the worsened RowHammer vulnerability. And there is a significant gap between the best mechanism we have and the ideal mechanism. So it also shows significant opportunity that we partially seized later on, and we have better mechanisms now that falls in between. So RowHammer is a technology scaling problem, as we show with experimental characterization data in this 2020 paper. And finding a good solution to RowHammer is difficult, and it will be even more difficult going forward. So here is a cartoonish comparison of different vulnerability levels. So again, I'm going to talk about this metric HC first. So this is essentially the hammer count. You see the first bit flip, number of hammers to the first bit flip. So in the extreme left side, we have HC first as like infinite. So no matter how much you hammer, you do not incur any bit flips in your DRAM chip. And on the on the right-hand side, HC first is 1, which is like DRAM is doomed. Every access results in a bit flip. So this is the spectrum we have, and this data shows that like which set of DRAM chips fall into what category. So based on our characterization results in ISCA 2014, we observe like 140K around for DDR3, right? And then in ISCA 20, these DDR3 results got down to 24K. And the only difference in between is the technology not scaling. Now we have like denser chips. We have more gigabytes in a given chip. And you see like different results for LP DDR4, DDR4, and HBM2 as well. None of them are like really good. So, so we showed this in 2020, and starting from 2016ish, DRAM manufacturers were claiming that our new DRAM modules do not have the RowHammer problem. We solved that internally. You don't have to worry about that. And when you ask them, or when you look at their documentation of how they solved it, they talk about a mysterious mechanism called TRR, target row refresh. So target row refresh is essentially observes your memory access patterns and then finds out potential victim rows, and it needs to refresh those rows in a targeted way. But this is very high-level explanation, and you do not see any further description, any details about these mechanisms, because it's considered as like proprietary knowledge and it's some corporate secret. They do not reveal it. So you have two options. Either you trust them and then you do not implement anything in your mechanism, you stop the research, assuming that DRAMs are fixed now, or you can get those new DRAM chips and then do characterization on top of that. So this is the work that does that characterization. It's also published in ISCA, sorry, not ISCA. This is Security and Privacy Conference in 2020. And it's a collaboration between our group and Free University of Amsterdam. Kaveh Razavi is also, at that time, I guess he was there and then he came here. So it's a ETH paper. You can be proud of that. So it shows that what DRAM manufacturers implemented inside their DRAM chips is a poor RowHammer solution. So there's a solution there, but you can easily walk around that. So this is the first work to show that TRR protected DRAM chips are vulnerable to RowHammer in the field. And the mitigations advertised as secure are not actually secure. And it introduces a new memory access pattern called many-sided RowHammer attack that you can use to bypass these mechanisms. So idea is that you hammer many rows, so it overwhelms the internal counter logic that they implemented inside the DRAM chip. And then this implemented TRR mechanism cannot figure out which row you're attacking. And it goes and refreshes the wrong rows. And as a result, you have bit flips in the row you actually want to have bit flips. So this Trespass work partially reverse engineers the TRR and PTRR. P stands for pseudo mitigation mechanisms implemented in DRAM chips and memory controllers. And it provides an automated tool that can effectively create many-sided RowHammer attacks for DDR4 and LPDDR4 DRAM chips that you can use to induce bit flips. So here I can just talk about this four-sided probably. So this is a cartoonish picture of how your DRAM array looks like. So these red rows are aggressor rows, and the blue rows are your victim rows. Excuse me. So you allocate your rows in this way that it alternates between aggressors and victims. And if you increase the number of aggressors, now the DRAM chip needs to keep track of the activation count of more and more rows. And they have only a limited number of counters inside the DRAM chip, which is a dumb design. But that design decision is there because of some cost concerns. And as a result, you overwhelm it. And here in this data, in these three plots, they belong to like different modules. So on the x-axis, we sweep the number of aggressor rows we have in this attack or access pattern. On the y-axis, we have the number of bit flips we have. So as you can see, up to like 4 aggressor rows for this plot, you do not observe any bit flips. The reason is that the counter mechanism they implemented inside that DRAM module can keep track of those 4 aggressor rows and refreshes their victims. So as a result, you don't have bit flips. But the moment you actually introduce the 5th aggressor row that you concurrently hammer, they cannot keep track of the 5th one, and then you have a lot of bit flips. And as you increase the number of aggressors, since you have a limited time window, you have like smaller hammer counts per aggressor. So as a result, you have some smaller bit flip counts. Okay. So, and this behavior is different from chip to chip. Yes. Yeah, it's a good question, actually. I don't remember the reason. Yeah. Yeah, the behavior I explained is more like in here. So from 9 onwards, you have a like general decreasing pattern. I'm not sure why we have a second peak here. Yeah, I need to check the paper, actually. I don't remember that. Good question. Maybe we should put the answer to Moodle. Okay, so in this work, this work, tests many DRAM modules from like 3 major manufacturers, and you see the best many-sided RowHammer access pattern in this column, for example. In some of them, it doesn't work. Some of them, like you need like hammer 19 rows, some of them 10 rows, and you have like a lot of bit flips basically as a result. And they tested several commodity devices, like these are some phones, tablets, whatever, and they use the DRAM chips, right? And these are the manufacturing dates, and you see that some of them actually were already vulnerable to this attack. So you can mount some system level attacks that perform this kind of memory access pattern, and you have bit flips on these devices, so they're compromised. And you can use these memory access patterns to attack to page table entries, to steal some RSA keys, and to gain pseudo privileges on these devices. And these are the attack time that you need. So you can get like a few minutes of attack, or like around 1 minute of attack for this module, for example, gives you the SSH key that you need. Okay, so they find out that 13 out of 42 tested DRAM modules are vulnerable. 5 out of 13 mobile phones are vulnerable. And these results are just scratching the surface in a way that the characterization study here is not super rigorous. Later on, we did another work, a follow-up of this work, that actually delved into more details and did a way more rigorous reverse engineering study that actually find out that there's more room for uncovering more vulnerabilities. So this Trespass work in 2020 essentially showed that RowHammer is still an open problem, and security by obscurity, the way that DRAM manufacturers did that, like just saying that our chips are safe, there's no RowHammer, but we do not tell you what the security countermeasure we take here. So this is what we call security by obscurity. It is likely not a good solution because there are many smart security people here and there, and they can find ways around these not very secure mechanisms. So after 2020, we also had some improvements in JEDEC documents. So they release near-term DRAM level RowHammer mitigation and system level RowHammer mitigation documents. They implemented new commands called refresh management and a new mechanism called PRAC that we will talk in detail tomorrow. Osan will, he's in the back. He will be here tomorrow talking about the details of these mechanisms. But I just wanted to mention here now because this is some exciting improvements from the industry side. Because if you look at the trends of this JEDEC consortium and their task forces, they have like many bodies in this consortium. There are like system manufacturers, some software companies, DRAM manufacturers, and to make a simple change, basically, you need to convince all these parties, and they should be on consensus on something so that there is some new requirement in the following DRAM communication protocol. Let's say you move from DDR4 to DDR5, and you want to add a new functionality or new timing constraint. It's quite hard to do. You need to convince many people. And these works, especially in 2020, played a huge role, actually, convincing people. And then they actually took some solid steps to solve this issue. The next work that I mentioned is uncovering in DRAM RowHammer protection mechanisms. This is the work that followed up Trespass, where we do a rigorous reverse engineering study. Basically, we use the data retention failures as a side channel to understand if a DRAM row is refreshed or not. So let's say you hammer a row, and then as a result of this hammering, inside the DRAM chip, the mechanism triggers a refresh, and then you refresh the victim row. So you can see if this row is refreshed or not by characterizing data retention failures. And this is a full-blown reverse engineering methodology that resulted in completely reverse engineering TRR mechanisms of different DRAM modules. And it crafted targeted access patterns to those modules. So they test 45 different modules by using this methodology. And they show that 99.9% of the rows in a DRAM bank experience at least one RowHammer bit flip. So you basically, at this point, reliably work around the deployed mechanism over there. So it's essentially ineffective. And ECC is also ineffective because when they look at the distribution of the bit flips, they can see up to 7 RowHammer bit flips in a 8-byte data word. So it's quite high density of bit flips that you can protect with some practical ECC schemes, basically. Yeah, sorry. So basically, you bypass ECC with these new RowHammer access patterns, and yeah, conventional DRAM ECC cannot protect against new RowHammer access patterns. So this also put a dot to the discussion about like if ECC is enough for RowHammer protection. So today you can fairly confidently say that ECC is not enough. We need additional mechanism on top of ECC. Now, if you think about it, actually ECC is there for the bit flips that are not very predictable, and they happen randomly, and the bit flip probability is uniformly distributed across cells. So in those kind of cases, and if your bit flips happen rarely, or like you have a very low bit error rate, then ECC is quite effective, right? So those are error mechanisms like soft errors, like you have a particle strike and then 1 bit flips and then you correct it. But in RowHammer case, you actually can craft memory access patterns. You can target some DRAM cells. You can predictably and repeatedly induce bit flips in some cells more frequently than others, for example. You can change the data pattern. You can redirect your aim of bit flip to different cells. So all these things are making RowHammer bit flips nature different than the other bit flips that we protect from by using ECC. So like in high level, this kind of chain of thoughts also suggests that ECC is not effective or not a very good fit for RowHammer bit flips essentially. But now we also have some experimental data backing up this. So next, I will talk about new RowHammer characteristics that we found out after 2020. But before doing that, are there any questions or about these two papers or on the DRAM mitigation, RowHammer mitigation mechanisms? No? Okay. Let's continue with new RowHammer characteristics then. So this paper is published in Micro in 2021. It's also one of the chapters in my thesis, so I love this paper. So here what we do differently is that we look at RowHammer sensitivity to 3 different properties. Temperature, aggressive row active time is a very low level definition of that. I would just say memory access pattern at high level, and also victim DRAM cells location inside the DRAM chip. And we do that to find effective and efficient attacks and defenses. And we test 272 DRAM chips from 4 major manufacturers in the study. We add Nanya on top of Samsung, Micron, and Hynix. And we come up with 6 major takeaways, 16 null observations. And we summarize those by saying that RowHammer bit flips are more likely to occur in a bounded range of temperature. So it's quite interesting, actually. It's not like you increase the temperature and everything gets worse. Sometimes increasing temperature reduces the probability of having a bit flip in a DRAM cell. And if you keep aggressor rows on or open or active for longer time than the minimum amount of time, you can reduce the number of hammers you need. I will talk about all these, and tomorrow also we will have a more elaborated lecture on this. And you can also find certain physical regions of memory that are more vulnerable to RowHammer than the others. And we show that our observations can inspire and aid more effective attacks and more effective defenses, efficient defenses as well. So it's better to know, right? If you know all these sensitivities, then you can improve your attacks or defenses. We do not want attackers to improve their attacks. We want to achieve like better defenses, but it's also like you need to study both to do that. Okay, so here's an example that we will talk about in detail tomorrow. Yeah, it will be obvious soon. Why? So we're comparing two access patterns here. So assume that these black vertical these lines are the times where we have a row activation for the aggressor row. So we activate the aggressor row here, and then in this yellow window, row A is active during that time, and then we close the row. And you have to do this because when you activate the row, there's a minimum timing constraint that you need to wait until you close the row. And then here you activate, here you close, sorry. And then you activate the other row. So let's say we are doing double-sided attack, A and B, we keep hammering. And then you hammer B, and then you close B, and then you activate A, close B, pre-charge, and close A. So if you do this as frequently as possible by the minimum timing constraints, so this is known as the most effective RowHammer attack based on the prior experimental data. If you remember the activation interval plot that I showed from 2014 paper, as we increase the time between two activations, the bit flip rate, bit error rate is reducing. But here in this study, what we showed is that if you actually use this time to keep your aggressor row active for longer time, then you can actually significantly reduce the number of hammers that you need to perform on these rows to induce a bit flip. So now, as a result, your HC first, or the minimum activation count you need to induce a bit flip, gets reduced significantly. And by doing that, let's say you have this information and you have this characterization data, 1 second, and the deployed mitigation mechanism in your system does not account for this kind of effect. Then you can easily bypass the defense by reducing the activation count, because it might be configured for a higher activation count. I can get your question now. Okay, so are you asking about the experimental methodology in this paper, or in a more realistic scenario in a real system? Okay. Okay, so the question is, how can we keep rows active longer in a real system? So in a DRAM array, if you remember from the last week's lecture, you have the DRAM array and you have a row buffer, right? And internally you access the DRAM cells in a DRAM row granularity. So when you activate, you fetch all rows data to the row buffer. And then as you have column accesses, reads and writes, you serve from the row buffer. And this activation, and once you want to close the row and activate another row, you need to wait for closing and then open the other row. These all add latencies. So I'm just talking about like general background of DRAM. And we do not want to pay for these latencies in like, just forget about RowHammer, think about benign workloads. We do not wait for these latencies so that we can serve our memory requests faster, so that our application can keep going, and then we can achieve high performance. So to do that, to ensure that we don't have to activate and pre-charge rows very frequently, the memory controllers exploit the locality inside the row buffer. So if you have two requests that are targeting the same row, even if they are like in different order in your queue, let's say, like first come, first serve queue, if your row buffer is open, you keep servicing these memory accesses, so that later on when you want to access the same data, you don't have to open the same row again. So this is called row buffer locality. And to leverage row buffer locality, memory controllers tend to keep rows open for some time, in case like new requests will come to these rows. And in real systems, what we do is that we access to a column in a row. a row is like as large as 8 kilobytes, right? And column access is in the granularity of like 64 bytes. So you have many of these columns inside a row. And what we do is like we access different columns with some time delay in between. So that the memory controller thinks that this row is quite hot now. It keeps getting accessed. So we need to keep it open for longer time. So it's a performance optimization that you can actually exploit for your attack, basically. Does that answer the question? Okay. Yeah, so in the yeah, so as long as the row is open, it's connected. So it's actually not decoupled in current architectures. If the row is open, so if the row buffer has your rows data, your row also stays open. So basically your word line is asserted. So your DRAM cells are connected to your sense amplifiers. And whatever you write to sense amplifiers, propagating back to the DRAM cells themselves. So that's the reason that everything is on and the word line remains asserted. And that's the main thing actually that creates this effect. We keep a high voltage on the word line so that it keeps attracting or causing electrons move around. That's a very good mitigation, yes. Maybe I should repeat. Potential mitigation is to decouple the DRAM array from the row buffer so that you can keep access into the row buffer, but you can close your DRAM row. And it comes at the, so it has trade-offs as well. What if you decouple it, you deassert the word line, you close the row, you have your data in the row buffer, and then you receive a write. Now you need to open the row again and then propagate the write back to the DRAM cells, right? So there's this trade-off. Also, for decoupling, you need to implement new isolation transistors between the row buffer and the DRAM array. So it also costs some area cost. And there's a, if you're curious, I can refer you to a very recent paper called Hi-Fi DRAM from Michele Marazzi, a PhD. He also graduated actually recently in ETH from Kaverazavi's group. He actually looked into the, so they did some like investigation on how DRAM chips are laid out. And they showed that like adding a wire even increases cost a lot, let alone like putting a lot of transistors there. So there are some like cost-driven concerns and also performance concerns of decoupling. But for addressing this issue particularly, yes, it's a good solution. Okay, so another aspect of this paper was about like looking at the spatial variation across different DRAM cells in a DRAM chip. So we observed that, let's say you look at the 10% most vulnerable DRAM rows, and you need some activation count. Let's say, let's parameterize it, HC first, to induce bit flips in this like most vulnerable 10% of the aggressor rows. DRAM rows. For the remaining 90% of the rows, you need at least double that activation count. So you don't have to protect all parts of the system or DRAM chip in the same aggressiveness, right? You don't have to protect, if you configure your mechanism to behave like for the worst case among your DRAM rows, then you end up overprotecting a lot of rows. And then it comes at a significant performance cost. And for some mechanisms that implement some sophisticated metadata management structures, it also increases their area overhead. So you can get rid of those by leveraging this kind of circuit level observation. And another thing that I mentioned about the temperature is that DRAM cells are vulnerable to temperature in a bounded temperature range. So as we increase temperature from left to right, there are two bounds, like a lower bound and an upper bound. In between, we observe bit flips in a given DRAM cell. But outside of this range, we do not observe bit flips at a particular hammer count for a given DRAM cell. So basically, we can optionally, dynamically retire some rows, basically, based on our system's temperature level, for example. So there are this kind of improvements that we can come up with. I can get some questions. You were first, yeah. So the question is, why do we have this vulnerable temperature range? In high temperatures, do we have the memory control refreshing rows more frequently? And is that mitigating bit flips? The answer is no. But this is a very good question. Like wherever I present this observation, I keep getting this question from DRAM experts. So very good question. So the reason is not that. We know that because in these experiments, we do not have DRAM refresh. We do not have memory controller. We test DRAM chips in an FPGA-based infrastructure, so we have full control on everything. We know exactly when a row is refreshed, exactly when a row is activated, and that is not the case here. So this is this goes back to I think I don't have backup slides for that, but this goes back to some circuit level phenomenon called trap-assisted charge leakage. So basically, inside your DRAM cell, in particular locations, you have some traps that electrons can get in and trapped. And then once it happens, you exacerbate the charge leakage inside the DRAM cell. So you lose your charge faster in your capacitor that causes the bit flips. And when you do the physics level simulation of this particular error mechanism, it has this behavior actually. So there are some circuit level works based on some TCAT simulations that show some similar behavior as well. Based on your traps characteristics, at high temperatures, electron does not get into trap. It just like moves across. And it causes like this kind of weird behavior. And when we look at this vulnerable temperature range across DRAM cells, it also varies a lot. So there are cells that are only vulnerable at like 50 degrees, for example, Celsius. And then there are cells that are only vulnerable at like 70 degrees Celsius. So it's very hard to generalize. And it makes everything much more complicated in terms of like profiling your DRAM cells, understanding their vulnerability limitations, and all that. So it's quite a curious phenomenon still to me. I hope this gives some sufficient answer to your question. There was another question. Yeah, it can be very narrow. So the question is like, how large is temperature range from DRAM cell to DRAM cell? It can be just like 1-2 degrees Celsius, or it can be like 50 degrees Celsius large. Like, let's say from 50 degrees to 90 degrees, it's vulnerable, for example. There are like all sorts of behaviors across DRAM cells that we can observe. Okay, let's move on. Yeah, there's a more detailed talk that is as long as 21 minutes. I also gave a full hour lecture on this. I guess I can add that slide later on. So we have more RowHammer analysis. So this is another paper that's part of my thesis. So I also like this work. Here, what we do is we change the voltage level inside the DRAM cell. So here is a picture of our infrastructure. So we have an FPGA-based infrastructure. We program this FPGA with a design that is written as like a highly modified version of SoftMC here. Now it's called DRAM Bender. Tomorrow we will talk about that as well. So we have actually many instances of this infrastructure in ETZ building, and you can get hands-on if you're curious. If you want to test different access patterns or changing different things and want to observe like what other behaviors we have in DRAM cells, there are a lot of undiscovered things, we believe. You can just get hands-on if you're curious. So here we have the DRAM module. We have a temperature controller that keeps the temperature stable for DRAM chip. And we have an external power supply that allows us to play with some voltage level on some power rails. So in this particular case, we changed the voltage on the word line of DRAM cells. And we show that when we reduce the voltage on the word line, Now you have a smaller voltage swing or toggling on your word line voltage as you activate and precharge rows. So in the to give an example, in nominal DDR4 constraints, you have to provide like 2.5 volts to your word lines, for example. And once you assert and deassert, the difference is 2.5, right? And if you scale down this power supply to, let's say, 1.7 volts, then you have a smaller voltage toggle on your word line. And this voltage toggle actually is the reason or the thing that triggers RowHammer bit flips. So what we expected and observed is that when we reduce this magnitude of this voltage toggle, we can reduce RowHammer vulnerability. And as a result, we observed that we can reduce the number of bit flips in a test. And also we can increase the necessary hammer count to induce a bit flip quite significantly. And this comes at the cost of increasing the row activation latency or memory access latency and reducing the data retention time that requires you to refresh DRAM cells more frequently. But it turns out that the current timing constraints that we get from data sheets already have a very large safety margin called guard band. So if we just use the nominal timing parameters, everything works fine for most of the chips. So there's a full talk about this as well. And I think the rest we will cover tomorrow. Not rest of all slides. The other characterization works. So as I said earlier, we also tested some HBM DRAM chips. By the way, is there any question about the voltage scaling work? I'm already done with that. No? Okay. So we also tested some HBM chips recently. As I said, it was published as a short paper in 2023 in a DSN workshop. And then as a full paper, it was published again 2024 with an extended version with more data, of course, with more rigor. And we observed that HBM2 DRAM chips are also quite vulnerable to RowHammer. Unfortunately, the current like industry standard is like HBM3, HBM4, but in the FPGAs that you can get today, you can only get like HBM2. So that's why we tested HBM2 in this work. I guess going on, we will also test like newer HBM chips, and I guess you can also guess at this point that the RowHammer vulnerability will turn out to be even worse. There is another paper that was published in HPCA that shows the spatial variation that I will cover tomorrow. And with that, we can done with the understanding part of the post-2020 works. And we will move to some new RowHammer attacks and solutions. So half double is a new memory access pattern that Google found out. Basically, So I think this gives me the nice pictorial representation, so I can talk about this. So in classic RowHammer, let's say we have a single-sided attack, meaning that we keep hammering a single DRAM row. So this is our aggressor row, and then the two adjacent rows on above and below are our potential victim rows. So we induce bit flips in these, right? So this is how classical RowHammer works. And once you have the on-die TRR mechanisms implemented inside DRAM chip, what happens is that since you hammer this aggressor row quite frequently, they keep refreshing these victim rows, right? So you do not observe bit flips in these victim rows. So the question is, if I keep accessing this aggressor row very frequently, and I trigger some victim row refreshes targeting these immediate adjacent rows, can I hammer these immediate adjacent rows to induce bit flip in the two rows distance? The answer is yes, but not very straightforward. So you hammer this a lot, and you hammer this a little bit, and also to help you actually, the on-die TRR mechanism also hammers this B thinking that it's protecting B because you're attacking A. So you have some activation count accumulated in B, and this A also has some disturbance induced to C here in 2 rows distance. And when you accumulate these disturbance effects, you can induce bit flips at C. So this is a new attack pattern that the deployed solutions did not account for. So this was able to bypass them basically quite reliably. So this was published as a blog post in 2021, and then as a full paper in Using Security in 2022. Another very interesting work is, so yeah, I really appreciate this work actually. So this is called Moesi Prime. So in this work, the authors basically went to Microsoft servers, and then they looked at the workloads access patterns to memory, and then they analyzed like this is a huge rigorous analysis of like snooping what is going on in the DRAM communication, right? And they find out that even if you do not have any attack in your system, you might end up hammering some rows and inducing bit flips. And when they started like tearing apart the system and why this happens, it turns out that in some chips, the Moesi protocol, I need to pause here actually and then ask you if you're familiar with cache coherency. Okay, so Moesi is a cache coherence protocol. Many of you are familiar with. You can also check the paper, it explains it. And we have lectures about Moesi for sure, so you can learn from there as well. So the Moesi protocol in some DRAM chips is not really implemented in the best way possible. So basically, for sustaining coherency, you might end up invalidating some cache blocks and then writing back some cache blocks very frequently to the DRAM chip. And then it causes, so with certain accesses to caches, you can make this even worse. It causes accessing a lot of, some DRAM rows a lot of times. So you end up hammering some rows unintentionally. And this is not even like a workload that a user runs on a system, right? It's just like the hardware components themselves are doing this. So this is a very good example of like, we have to, when we design new systems, we need to look at like all aspects of this, and we need to avoid this kind of unwanted behaviors. So to me, it has some parallelism with the other attacks, for example, that we keep suffering from, Spectre and Meltdown. Have you heard about Spectre and Meltdown? Basically, it's like for performance improvement, you have speculative execution in your microarchitecture, and that causes some observable intermediate states in your architecture, and a malicious person can understand what you're doing, and it can create some side channels, right? And in this case, you don't even need a malicious user that's doing anything wrong. Basically, some improvements, some implementation you did in your architecture causes this hammer and access pattern. So it's fascinating. We need to really like design systems by considering like microarchitecture, memory subsystem, the software stack, all of them together. So the new and better architectures should come with a holistic approach. Yeah, another paper, 2021, also part of my thesis, but I think I'm not going to go into this very deeply. It was published in HPCA. It's a RowHammer mitigation mechanism that basically selectively throttles the memory access patterns that are performed in some hammer and access pattern. Before going into that, do you have any questions so far? No? Okay. So we identified 2 key challenges. Okay. Maybe we should take another break, but let me quickly check something. Okay, maybe I can cover this and then we can take the break. So am I still sharing the screen on Zoom? Okay, that's good. So we looked at the existing mitigation mechanisms of that time, and we identified two key problems. One of them is scalability with worsening RowHammer vulnerability that we keep talking about. The other one is compatibility with commodity DRAM chips, and I will explain it here. So, okay, this is not explaining the problem, but I can verbally explain it. So basically, when you hammer an aggressor row, you need to refresh the rows that are physically adjacent to the aggressor row, right? But inside DRAM chips, there's a row address mapping that can scramble the logical row addresses in the physical layout. So row A+1 might not be next to row A, for example. And this is some proprietary information. You don't have access to this information. And there have been a lot of RowHammer mitigation mechanisms that are proposed to be implemented inside the memory controller that performs victim row refreshes, which is not really practical without having that information. So here in this work, we tackle that problem. That's the challenge with compatibility with commodity DRAM chips. So when a RowHammer attack hammers a row A here, so it might have induced bit flips in immediately adjacent rows, but BlockHammer, our mechanism, detects this RowHammer attack using some area-efficient structure called balloon filters, and it selectively throttles the accesses targeting this row A only. So all other accesses are serviced as usual. Nothing changed for them. But for the accesses that are targeting row A, you slow down that. And then as a result, in an extended time window, you don't have many accesses to row A, and bit flips do not occur in the victim rows. And in this scheme, you don't have to know which row is adjacent to which row. We also do the performance evaluation and show that BlockHammer can mitigate RowHammer bit flips with low overhead. So a takeaway so far is the main memory. So it's just reiterating it, right? Main memory needs intelligent controllers for security, safety, reliability, and scaling. I didn't talk about all those solution space. I can refer you to other papers as well going forward. But basically, like we have several solutions in the field, and they have their own trade-off space for in terms of cost, power, performance, and complexity. Some exciting news are like from 2023, ST Hynix published a very short paper. It's just like 2-page long, if I remember, that talks about both probabilistic and deterministic RowHammer mitigation mechanisms that they propose to be implemented inside DRAM chips. So you can assume that they are implementing those. So I'm just gonna skip this, and I show here that so they even show some die picture where you have a cell, an array of normal cells, and you have some RowHammer counting cells here, and some logic here that keeps accessing these like activation counters inside the DRAM chip and performing RowHammer refreshes. There's another paper from Samsung that proposes some in DRAM stochastic and approximate counting algorithms. And this paper was actually bypassed by the Google paper recently that I showed at the beginning of the previous session. And there's another paper that we had from, it was from 2021. Yes, it's from 2021. It's published in a workshop called DRAM SAC. That's pretty much the showing the state of the art in RowHammer for the past several years in the workshop itself. So it's a workshop collocated with this ISCA conference that is one of the top conferences in architecture. So in this paper, they propose a mechanism where you implement a row activation counter for each DRAM row inside the DRAM chip, and you exploit the DRAM cell's high density to implement all these counters at low cost. And that turns out to be the new addition to the DDR5 standards, actually. So DDR5 is a few years old, actually. If you go to the first documents, I think it's from 2020. But in 2024 April, like less than a year ago, right? It's just like this year. It got an update. And this update suggests that newer DRAM chips, DDR5, DDR6, going forward, will implement a RowHammer mitigation mechanism where you have a row activation counter affiliated to a DRAM row. And internally, you keep track of the activation counters in a hopefully better way than the previous implementations of TRR. And you perform these victim row refresh operations based on the activation counts quite on spot or like when needed. Tomorrow, Osan will talk about this whole prac mechanism, its trade-offs, pros, cons, and limitations. And we already analyzed it in a short paper that was published in this year's DRAM SAC. As you can see, Osan is the first author. We already implemented this in our simulation infrastructure called Remulator, actually. It's on GitHub. You can even like download and evaluate this new edition of DDR5 in your systems today. Of course, it's not like using your own hardware. It's a simulation environment, but you can understand the performance benefits or security limitations or performance overheads. So, okay, let's ask the question, are we now RowHammer free in 2024 and beyond? I see some faces doing this. Okay, yeah, I think you're right. Yeah, so it seems like we are not really RowHammer free or redisturbance free. So in 2023, last year in ISCA, we published another paper called Rowpress that I will talk in detail after the break. And it basically asks the question, what if there's another phenomenon that is based on DRAM redisturbance, different than RowHammer? So we all have all these like mitigation mechanisms over there, mitigating RowHammer bit flips. What if we have another error mechanism? So what happens then? And we actually found that error mechanism. Tomorrow, Hasan will talk about it in detail. I will also briefly explain it in the last part of this session. So are there questions so far? Okay, let's take another 10-minute break, if you don't mind, and then we can cover the rest of the slides quickly. Hello? Ismail, can you still hear me? Test. Can you still hear me? Is there a problem? Is good? Okay. Okay, let's close the door. Okay, so thank you a lot for coming back on time. So I'll sort of speed run the last part of this slide deck, but I'm doing this on purpose actually because we will have more elaborated lectures on these topics, or at least like most of these topics, tomorrow and in the following other lectures. So now I'm going to talk about Rowpress. This is something similar to RowHammer, but a different error mechanism that we have in the DRAM chips. That's another DRAM read disturbance phenomenon. So this paper is published in ISCA 2023, so it's quite recent. Not all people are still aware of this, but it's getting there. So it's something quite significant, and it's quite important going forward. So I'll just go over these slides in a high level, and then tomorrow we will have a more elaborated lecture. The first author, Hao Song, will be here, and he will talk about Rowpress. He will talk about a follow-up work of Rowpress and some circuit level simulation studies about Rowpress as well. So this is the high-level summary of this new read disturbance phenomenon. So in this paper, we demonstrate and analyze Rowpress. It's a new read disturbance phenomenon that causes bit flips in real DRAM chips. It exacerbates DRAM RowHammer vulnerability, but it is different than RowHammer vulnerability. And we demonstrate Rowpress using a user-level program on real Intel system as well. So you can even mount Rowpress, you can exploit Rowpress from system-level attacks. And we also discuss some effective solutions to Rowpress in our paper. And there are some follow-up works as well. So basically, what is Rowpress? Rowpress is a memory access pattern. It's a DRAM read disturbance phenomenon that we'll exploit by keeping a DRAM row open for a long time. So you can see the parallelism actually in the Micro 21 paper. I mentioned that if you keep a row open for a long time, you can reduce the HC first value or the minimum hammer count you need to induce the first bit flip. So it was a preliminary observation, if you will, in that paper. And in this one, we basically do a more rigorous analysis of such phenomena, such empirical observation, and try to understand what is the root cause of this and how this behaves under different conditions. So we find that these bit flips do not require many row activations. So you can achieve these bit flips by activating rows only a few times. And in some extreme cases, you can achieve bit flips with only one row activation. You activate a row, wait for a very long time, which is, I would say, not practical in current systems today. But if this phenomenon exacerbates, then it can be quite practical in the future. So, okay, let's look into this. So the question we asked in this paper, are there other redisturb issues in DRAM and other than RowHammer, we mean? And can we, like, so far, like there's a lot of focus on RowHammer, right? If there are some other redisturbance mechanisms, then the trade-offs might change. And mitigations work by detecting high row activation count for RowHammer. And can we use them for other potential DRAM redisturbance problems as well? So what if there's another redisturbance problem that we cannot actually mitigate by just like looking at the high activation count? So it makes our like such potential unknown redisturbance phenomenon can make our very sophisticated and provably secure mitigation mechanisms vulnerable or bypassable because of the basic assumptions of like requiring high activation count. So here, what we do is that instead of using a high activation count, we increase the time that aggressor row stays open. So we already went through this in the micro paper, right? And we observe that here you can see, if you keep a row open for 36 nanoseconds, you need to activate a row for 47,000 times to induce a bit flip. So now we look at the same bit flip, and we open the row 7.8 microseconds instead of 36 nanoseconds every time we open the row. And by doing that, we can reduce the necessary activation count from 47,000 to 5,000. So it's an order of magnitude reduction, right? And if you actually keep the row open for 30 milliseconds, then only one activation is enough. So open for 30 milliseconds, it's not very realistic, but it shows like where it is going, right? So in this work, we use a FPGA-based testing infrastructure. Again, we have an FPGA board here that is programmed with DRAM bander that we will talk about in detail tomorrow. And we have a DRAM module pressed against two heater pads from both sides. And these heater pads are controlled by a temperature controller, so we have the temperature stable as well. And we have a host machine that runs the tests and analyzes the experimental data. So we have full control on what kind of DRAM commands we are issuing to this DRAM modules, and we have fine-grained control over their timings. So every 1.5 nanoseconds, we can issue another DRAM command. And we observe that we test 164 DDR4 DRAM chips from 3 major manufacturers that cover different densities and revisions, so from different generations, if you will. And we observe that they are vulnerable to this new read disturbance phenomenon, Rowpress, and Rowpress significantly amplifies DRAM's vulnerability to read disturbance. And it has a different underlying error mechanism as well. So when we look at the change in the minimum activation count to induce the first bit flip, the abbreviation is a little bit different here, AC-min. We observe that we can reduce this necessary activation count 1 to 2 orders of magnitude in a practical way. So here on the x-axis, we have the time that we keep a row open for, like how much, basically here. So in the first column, we have we keep row open for 36 nanoseconds. This is the minimum you can do. And here 7.8 microseconds, 70.2 microseconds, and 30 milliseconds, like just these points that we selected. And it's an educated choice, actually, because 7.8 microseconds is, in these DDR4 modules, the time interleave between two refresh commands. When a refresh comes, you need to close the row so that you can perform refresh operation. That's why 7.8 microsecond is an important point. So at 7.8 microsecond, we can reduce the activation count from tens of thousands to just like single-digit thousands, right? And there's also an extended refresh mode in the modern DRAM chips that you can postpone refresh operations for 9 times here. So basically, you can practically keep a row open for 70 microseconds until in between 2 refresh commands. You can postpone refresh commands that much. And it results in a few hundreds of activations to induce the first bit flip. So it's quite significant reduction in a very practical way. And it's getting lower and lower. Please go ahead. Which timing parameters? Yes. Correct. Yes. Fourth one does not, because you need to perform refresh. So basically, you cannot keep a row open for more than 70 microseconds, 70.2 microseconds, because at that point, you need to close and refresh. I'm not sure if it's a correct place to get into that discussion, actually, but I can briefly mention that. There are some works also in the past that show that not all rows need to be refreshed every 64 milliseconds. So there are some rows that can retain their data for more than 2 seconds, for example. You don't have to refresh those rows. And prior work already shows that you can get significant performance benefits if you leverage this heterogeneity in your system. And if you imagine that kind of system, for example, maybe you don't have to perform a refresh operation after 70.2 microseconds. So maybe the maximum realistic time window can be something between this, maybe even 30 milliseconds. So yeah. So basically, like, yeah, with today's commercial devices, it's not possible, but it's important to look into, basically. And I hope that you're familiar with this cartoonish picture by now, because I already showed it before. So on the left side, we have everything good. On the right side, we have DRAM is doomed. And you can see that with the new DDR4 DRAM chips, we can induce bit flips with 380 row activations if we keep rows active for like the nominal refresh, to abide with the nominal refresh interleave and interval. And in HBM2, it's even worse. 335 row activations are enough to induce bit flips. And if you exploit the extended refresh rate, where you can postpone the refreshes, the story becomes like this. So 51 activations is enough to induce a bit flip in a new DDR4 DRAM module, and 123 activations are enough to induce a bit flip in HBM2. So these are quite low, and you can even observe easily benign workloads reach into these activation counts. Of course, they do not keep rows open for 70.2 microseconds, but just being those numbers in the same ballpark is something significant that shows that we need to actually immediately take some precautions, some countermeasures to this. So essentially, it amplifies read disturbance in DRAM. It reduces thresholds quite significantly. In extreme cases, only one activation is enough to induce bit flips. And we observe that as you increase temperature, Rowpress gets worse. So it's different than RowHammer. In RowHammer, we had a bounded temperature range, right? Here is increased temperature, it gets worse. So it's a different, it has a different behavior with temperature. And we observe that it's actually different than RowHammer because of this phenomenon, and also because of some other behaviors that Hasan will talk in detail about. So it affects the different set of cells compared to RowHammer and retention failures. Not the same cells are the most vulnerable ones for all those three mechanisms, and it behaves differently. So we also showed that we can exploit it on real system on an i5 machine with a DDR4 module connected to that. And what we do is exactly what I described in the previous question, actually. We basically keep accessing to different columns inside the same row so that the memory controller is motivated, or there's some incentive for the memory controller to keep the row open longer. And actually, on the x-axis here, you see that we access different number of cache blocks in the same row as you go from left to right. So in the leftmost one, we only access one cache block. So it's a RowHammer attack, right? You activate the row, read one cache block, and then pre-charge the row, activate again, because you want to maximize the activation count. And here, we keep accessing different number of columns, and we see, so on the y-axis, it's the number of bit flips that we'll look into, and until like we access 32 different columns in a row, we don't observe any bit flips in this test. So basically, in this particular test, we show that there is this DRAM cell, set of DRAM cells or DRAM chip, DRAM row, that we cannot induce bit flips by using RowHammer alone. But if we use Rowpress to exacerbate DRAM read disturbance, then we can have significantly large number of bit flips. Okay, so we propose some adaptations to the existing mitigation mechanisms in this paper to address Rowpress as well. So basically, we basically limit the maximum row open time by the memory controller scheduling policy. And we also reduce the thresholds that we use accordingly, so that we just like modify the existing RowHammer mitigation mechanisms to behave a little more aggressive, and we close the rows at some point when it reaches to some threshold, and we can mitigate it. And we show that we can do that at very low performance overhead. There are many more results and analysis in this paper, and there are more things that we need to discover as well. So if you're curious, please refer to this paper, read it through, and please attend the lecture tomorrow as well, so that you can have a better understanding. You can ask your questions directly to the first author as well. And we have like lots of empirical observations, and we have suggestions for mitigations, and all this experimental methodology, simulation, infrastructure, everything is open source on GitHub, so you can also dig into that as well. So this is the full reference to paper, and we have more to come. Again, two major directions: understanding read disturbance and solving read disturbance. We need to invest on both directions. And as I referred to earlier, in 2023, we published this fundamental understanding and solving RowHammer paper. It's an invited retrospective paper that summarizes the recent advancements. But after 2023, as I showed earlier, like we have more advancements in the field. It's a quite hot field. We have a lot of papers coming up. You can see just in 2024, a lot of papers. So this is one of them that we'll talk about tomorrow as well, along with Rowpress. So in this work, we combine RowHammer and Rowpress memory access patterns to achieve a more effective attack than both. We have some other papers that try mitigating so it's actually a bit abrupt here, but I will talk about this, I guess, later on in the memory access latency and refresh lecture. So basically, there are more RowHammer mitigation and RowHammer attack papers and RowHammer characterization papers in the field in the recent years. So this paper in particular talks about the limitations of the communication between the memory controller and DRAM chip in today's setup. And it's important to actually revisit, so that I talked about, for example, the internal row address layout inside the DRAM chip, and we do not know that from the memory controller side. It's a limitation. Another limitation is that inside the DRAM chip, you implement some TRR mechanisms. You need to perform a lot of refresh operations, but the DRAM chip does not control its own timing. So the memory controller controls its timing in a very fine-grained manner, and it doesn't have the same information as the DRAM chip. And this causes some difficulty in like performing all those to fit all the operations in a time window, basically. These scheduling decisions are getting way more complicated when you have this poor communication between the DRAM chip and the memory controller. So this work talks about all those, and also on the IECC as well. So I will refer to that. I guess going forward, we will talk more about these kind of things. So this is another paper in the same direction. Okay, so I guess I have to explain this paper. So it's important at this point. So as you see, like going forward, DRAM chips cannot be just like the old usual DRAM chips that we can control everything from memory controller. They need to be smarter. They need to be more robust. They need to be more reliable. And that requires, as we go forward, to implement better maintenance mechanisms inside the DRAM chips. And this is important because, as I said earlier, doing any simple change in the DRAM and memory controller communication protocol is a very painful and high latency process because of convincing all the different parties in the consortium. And as a result of that, we have some maintenance mechanisms that's implemented in a huge delay. So we discovered RowHammer as a widespread phenomenon in 2014. And the first promising solution came out in 2024. So after 10 years. So it took 10 years for the communication protocol to adapt to this kind of, or address this kind of need. And this paper is proposing a solution to this whole problem in the industry. So this is called self-managing DRAM. It enables autonomous in-DRAM maintenance operations. And the key idea is that we just need to let DRAM take some time off when it's needed to perform the maintenance operations. So it prevents the memory controller from accessing the DRAM regions that are under maintenance by rejecting the row activation commands to those. And it's a simple addition to the memory communication, the DRAM communication protocols. And basically, we add a signal from DRAM chip back to the memory controller called ActNAC pin. And I think you will find some similarity between this pin and the signal that Osam will mention tomorrow about the RowHammer solution. So basically, when DRAM chip decides to do some maintenance operation, this maintenance operation can be a refresh operation, can be RowHammer mitigation, can be memory scrubbing, can be anything. It basically blocks a memory region. And if memory controller tries to activate a row in that memory region, it sends a signal called ActNAC. So memory controller understands that activation is not performed, and it does not try activating for some time, and then it tries again. And by doing that, we can enable a lot of maintenance mechanisms. In this paper, we talk about 3 of them: DRAM refresh, RowHammer protection, and memory scrubbing. And you can implement like a variety of all these maintenance mechanisms, actually. And our goal is to ease the process of enabling new DRAM maintenance operations, and we show that we can easily implement those without any additional changes in the memory communication protocol. And by doing that, we can also even improve performance while enabling all these maintenance operations. So Hassan is the first author of this paper, who is an alumnus of Safari, and he has a full talk on YouTube explaining all the details. I want to encourage you to go there and listen to that, and also refer to the paper and understand details as well. It actually talks about the underlying and overlooked problem of the DRAM industry. In a sense, it's quite important and like it's really interesting going forward to enable better, more robust DRAM chips. So I'm not going to get into this other paper. Before this, are there any questions about self-managing DRAM or the other things? Yes, go ahead. Yeah, so yeah, I didn't get into details. Basically, when you do maintenance operations inside the DRAM module or DRAM chip, then you have way more freedom of doing things in the way that you want, that works for you, than doing them in the memory controller. So one example is you can enable subarray level parallelism, for example. So inside the DRAM bank, you have hundreds of subarrays. And in the current communication protocol, if you refresh one row, 8 kilobytes of data, you actually block megabytes of data because like the whole bank is blocked during that refresh. But internally, you don't have to do that. You can leverage subarray level parallelism. You can access one subarray while doing the maintenance operation in other subarrays. So you can overlap latencies. You can hide things. You can skip refreshing some rows if they are not needed to refresh. You can track row activation counts in a way high accuracy compared to memory controller. So you can reduce the number of maintenance operations, and you can actually perform them in a lower latency as well when you do them in DRAM chip. Other questions? Okay. So we have more papers that are published this year. Abacus is a paper for RowHammer mitigation published in Usage Security in August. And Comet is an HPCA paper. It's also about RowHammer mitigation. Nisa in the front row. We'll talk about both of them tomorrow. Please attend the lecture. Spatial variation aware disturbance defenses is my paper that was published earlier this year. I will also talk about it tomorrow. And this is the reference to my thesis for like a nice summary in the related work, and also the projects that I talked about today are included inside this thesis. You can read it there as well. So one thing to mention on top of all these is that effect of aging on RowHammer bit flips that we do not know. So this is an ongoing problem. Nobody knows the effect of aging on RowHammer bit flips. So we urgently need to do more characterization works to understand how DRAM aging affects RowHammer bit flips. So we have some preliminary data that we published in the paper that I mentioned last, where the aging can lead to RowHammer bit flips to occur at smaller hammer counts. So what we did was like we kept hammering some rows for many days. And then we observed in a small fraction of rows that the activation count threshold can be reduced a little bit or quite significantly in some cases. So this is some motivational data. I'm not claiming that aging has a huge effect, but this is some motivational data that hints that there's something there. And if you can find what is there, it can be a really impactful work. So I want to encourage you to, do such studies. We have all the infrastructure if you want to use. We have an upcoming paper called RowHammer that reduces the performance overheads of existing mitigation mechanisms by throttling the suspected threats that will appear in Micro next month. So it's not published yet, but I can quickly summarize it. Our key observation is that RowHammer mitigation is some performance, has some significant performance overheads, and it's a new attack surface for exploits like denial of service. So you can keep triggering these mechanisms. So they keep the DRAM chips busy. So DRAM chip cannot service your memory requests. And as a result, you end up denying the memory service. And it causes a lot of performance overheads. It's a very charming attack for the malicious people. And our key idea is to throttle the memory access patterns of the hardware threads that keep triggering these maintenance operations. And to do so, we propose a new mechanism called RowHammer that detects the threads that repeatedly trigger these maintenance operations and limits their on-the-fly memory requests by limiting the cache miss buffers that they use. And we can implement it at near zero overhead with no additional memory access latency. And we can improve system performance quite a lot by avoiding or mitigating the effect of denial of service attacks. So probably after Micro, in a future session, we will talk about it in detail as well. So we have more solutions in the industry as well that we will talk about. You can, when you look at the programs of the major conferences in 2024, you can see a lot of papers about RowHammer. You have workshops fully about RowHammer. All the papers are about RowHammer in this DRAM security workshop. You have circuit level simulation studies that Hasan will talk about tomorrow. And in the upcoming Micro conference, we have a session dedicated for RowHammer with 3 RowHammer papers. So we have going forward more future robustness challenges, because as DRAM cells get smaller with technological scaling, we observe that the minimum hammer count to induce bit flip gets reduced more than 2 orders of magnitude, and it affects the memory robustness quite a lot. So memory is becoming less reliable and more vulnerable. So we need better mechanisms, and we can have other error mechanisms in the circuit level that we do not know for today, but we need to discover them so that we can mitigate their effects whenever they come. And for future main memory robustness, we need to look at DRAM, but we shouldn't stop with DRAM. We should look at flash memory. That's also very unreliable memory technology, but we have smart mechanisms around that that make it work. But it also gets worse, so we need to look at that. We need to look at emerging memory technologies. There are some like futuristic papers that were published. This one is published 2009, quite early, basically, that looks at the trade-offs of using phase change memory as the main memory. So I want to refer you to that as well. So the takeaway is that going forward, we need intelligent memory controllers, enhance robustness, and enable better scaling. We need to understand, architect, and design better testing methodologies for the memory systems. We need better infrastructures. These are some pictures of our infrastructures for DRAM and flash memory. And I'm gonna just show you a lot of bridges that have collapsed. So these bridges were not robust enough, and this is some disaster. And we do not want similar disasters in our computing systems. So we need intelligent memory controllers to avoid such failures. And main memory needs intelligent controls for security, safety, reliability, and scalability. And we need fundamental robust computer architectures. We don't need to have, we don't want to have just like temporary patches. Final thoughts. This is a sort of Byzantine failure where you can have undetected erroneous computation, and it's not something like you can fail fast and you can have a direct error message. You need to do a lot of characterization. You need to understand your circuitry really well, and erroneous behavior of the circuitry can be exploited and it can be used maliciously. So we need to avoid all of these. A reference to Byzantine generals problem, you can take a look at that if you're curious. And yeah, so this is not something new. Last thing, I promise. Before RowHammer as well, we had some attacks. Basically, you put a light bulb next to the memory, it heats up the memory, and then you have a lot of data retention errors, and you can attack systems like this. So this is a paper that was published in Security and Privacy in 2003. And with RowHammer, such attacks are much simpler, much exploitable, and they can be induced by the software. So there are a lot of news articles as well about that. So RowHammer set up a new mindset, and it renewed the interest in hardware security attack research. And it shows us repeatedly, actually, hardware security is important, and we need to understand our systems better. We have many RowHammer and Bitflip attacks. Tons of papers come every year, and many new RowHammer solutions as well, but more to come. So this shifted mindset in the mainstream security researchers, and now they are looking at the hardware as well. And it's also not a coincidence that the two groups that discovered Meltdown and Spectre also worked with RowHammer before. All of these are like related to each other. So there are more to come. In conclusion, memory reliability is reducing. RowHammer is a prime example of that. And it's the first example how a simple hardware failure mechanism can be exploited and become a widespread system security problem. Bad news is RowHammer is getting worse. And good news is we have a lot to do. So if you're curious, we have a lot to do. We have a lot of infrastructure available. You can come work with us. Okay, so I'm just gonna skip this because we are running out of time. And I'm gonna show you some Safari pictures. This is our group. We have newsletters. We have a lot of updates on DRAM read disturbance and also other topics that we're working on. And you can find our lectures, and thank you for the funders. And yeah, so you can access all the papers actually, essentially in this link. Please don't hesitate to read our papers. I encourage you to read our papers and also get hands-on with our tools. We open source everything on GitHub. And we have this new infrastructure for simulation Remulator 2. And the reminder that I keep talking about the FPGA-based infrastructure. Hassan will talk about them tomorrow. And we have a PNS course about this. And we have some other lectures already on YouTube that you can follow. And this is the story of RowHammer, only on the surface. For deeper knowledge, please come fresh to our lecture tomorrow. So don't get hammered tonight. And let's see you soon tomorrow and get into details more. I can stay and answer your questions, but we are out of time and they're catching another lecture, I guess, now. So I'll stay a little more to answer your questions, but we should wrap up the session here, I guess. Thank you very much.